Yeah, you got a little bit to go before that, but we're getting there. Um, all right, so we need to kind of do a couple things. One is sort of analyze the results from our card sorting experiments. So let's open up that spreadsheet. All right, so let's go to Canvas, get the link to the spreadsheet. And then we need to sanitize the data a little bit so that we don't have any of these division by zero issues. Um, all right, so here's what we got last time, right? All the card sorting. All right, so I'm going to go in and delete these things that are doing the division by zero error. Basically, it's trying to average nothing, and that doesn't make sense, obviously. Um, so let's get rid of that. Oops, get rid of that. Um, get rid of these two. And then we can delete these columns, and it should average the remaining the remaining numbers. Okay, so as we saw before, it was looking like the average for one suit was 15, the average for two was 42, 73, and then 108. Does that, I mean, seems roughly reasonable? Yeah. Okay. So now what we want to do is, well, a couple things. Let's graph them. So in order to graph them, I need to do 1, 2, 3, and 4 to be basically our x-axis. And then, man, this thing is really slow today. All right, and then it was 15.68, 42.51, 73.00, and 108.67. Okay, whatever. All right, and then we want to graph this. So let's graph here. So select those guys. And then we need to do, go up to one of the menus here, and it's the insert chart. And then it should kind of detect that I want to do a graph, because usually it's relatively smart. Okay, so there we go. Right, and okay, the chart's maybe not super illuminating, um, but in particular, then the other thing I want to do is, um, so how many of you guys have taken, well, really any science class or a stats or something where you've got some data and you want to fit a curve to it and say, all right, what's sort of a model that would explain this data? Yeah? So like a regression curve. Okay, so we want to do a regression curve. Um, and uh, in order to do that, right, we need to, so we've got our data. Um, and okay, so I'm going to change this to, let's see, we need to do chart editor, chart. Okay, and then we can go over to customize, right? Well, first off, let me change this from a bar chart to a, let's do a scatter plot. Okay, And then here for customize, we're going to do, let's see, series, data series, trend line, and the type of trend line we're going to say polynomial, and probably polynomial of degree 2. And I'm also going to show the R squared value, okay? Oh, wow, that is really good. And then let's see, we want to, right, okay. So what this did, right, let me scroll down a little bit so it's a little easier to see, is we've got our points of data, and then basically I tried to fit a parabola or a quadratic curve to it, or a polynomial curve. And in this case, I selected a parabolic, so a quadratic function, partly because I know that's what it's going to be. That's the best one for this model, or for this problem. But we can actually see sort of better evidence as to why that's the case. This R squared value basically is a measure as to how good our model fits the data. And R squared equals 1 means it's perfect, okay? Now, if you have only three points, then 3 points uniquely determine a parabola, okay? So if you only have 3 data points and you do a quadratic fit, it will always be perfect. That's just math, okay? Here we only have 4 data points, okay? So I'm actually a little surprised it's exactly equal to 1. But yeah, so if we had done this with extra pieces of data, now with the cards, this would have maybe been a little bit ridiculous, because what would we have had to do to get more data points here? You would have had to sort 5, 6, 7, 8 suits, and that's like 2 decks worth of cards, right? Okay, which at that point is getting a little bit ridiculous to do by hand, but you get the idea. Okay, so if we did this with a cubic, okay, so polynomial of degree 3, it would be perfect because we have only 4 data points. Okay, so again, that's just math. So there's no point in doing that here because it's not actually going to explain anything. Okay, but what I want us to sort of observe is that if this is a quadratic thing, then if we let n be the number of suits, okay, 1, 2, 3, or 4 is what we did, then the amount of time it takes is on the order of n squared, okay? Now, it's not exactly equal to n squared. There's some coefficients and stuff, but it's basically an n squared kind of function, okay? And in what we're going to sort of start talking about today, we don't actually care necessarily about what the coefficients are because, well, they're just coefficients, okay? Now, so what would if this is an n squared kind of thing, what would the actual equation of this polynomial look like? Actually, I wish it would show me the equation. Oh, there, that's what I wanted. And label, that's what I wanted. Label, custom, use equation. Well, there it is, okay? So the equation for this thing, let me just write it big up on the board so that we can all see it. So what was it? 2.21 n squared plus 19.9 n and minus 6.35. Okay, so I've changed it to n here instead of x just because we'll use n more often. It's just defaulting to x because it's Google Sheets. But whatever, that's just a letter. Okay, so what I want to kind of say is, in what sense am I justified in basically saying this equation 2.21 n squared plus blah, 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 blah. This is essentially n squared. Okay, so I'm going to write a squiggly line because it's not equal to n squared, right? I've kind of blown off the coefficient, and I've also blown off the n and the constant term, okay? Why is that, like, okay? So let's maybe think about this another way. If I handed you 1,000 suits of cards and told you to sort them, okay, and we plugged in 1,000 to this formula, right? That would give us our estimate as to how long it would take you. Which term dominates for large values of n? Yeah, the squared term, right? So for very large values of n, the squared term is the one that's going to be really driving things, okay? So it's maybe another way to say this would be like, you know, if Bill Gates walks down the street and sees a $100 bill sitting on the sidewalk, he actually loses money if he stops to pick it up, right? In the sense that he's so wealthy that his time is worth more than $100 to stoop down and pick up a $100 bill. Okay. And for that matter, would a $100 bill really change Bill Gates' wealth at all? Technically, it would, right? But like the percentage of his wealth that would be that $100 bill is so pathetically low that you might as well just ignore it. Right. Okay. It'd be like us picking up a penny, right? I don't know. I mean, there's the luck of it, and the fact that hey, I found a penny, and then you feel good. Oh, okay, yeah. So if you believe in those superstitions, then whatever. Okay, right. So anyway, so point being that $100 bill really has no effect. Okay, and so for this polynomial, we don't really care about this stuff for very small values of n, okay? What we want to kind of see is what's the expense of adding another suit of cards and then another suit after that and so on. Okay, so we're sort of interested in the long-term behavior of this algorithm rather than necessarily it for small numbers, okay? And for small numbers, yeah, all three terms matter. But if we start plugging in really, really big numbers for n, then the n squared term is really the only one we need to worry about, okay? All right, and so that's the sense in which I can say that this is sort of like squiggle n squared. It's essentially n squared. Now, there's a more technical way to say that, which I'll write and say out loud, okay? And of course, I left my chalk sitting over here. And unfortunately, we don't have computers and androids that I can just command to do everything. But yeah, so better get right on that and pull up a card maneuver. That's what it's called when you have to, yeah. You would know that, Cody, if you actually knew any Star Trek. Cody, yeah, yeah. Mm. If you watch every episode of Star Trek between now and the end of the semester and all the movies, I'll give you 10% extra on your grade. You'd be doing, if you did nothing but watch Star Trek between now and the final, you might be able to do it. Okay? Might. But your eyes would be bleeding when you came to the, right? So, all right. I know, right? So here's our definition. Okay, so here's our definition. Okay, f of n is said to be big O of g of n. Okay, means that there's some constant. We actually don't really care about the constant. So that for all n, f of n is less than or equal to m times g of n. Okay, so looking at this, when I wrote squiggly here, what I really meant is that, so let's call this function f, okay? Our function f that we got is O of n squared, okay? Because it looks like n squared, and if we thought about it hard enough, we could figure out the necessary constant to make it the case that that thing was always less than or equal to something times n squared, okay? All right, so, but it's, do we get the definition here? Okay, so this particular card sorting routine, okay, now I didn't tell you guys how to do the card sorting. There are clever ways of doing sorting we'll program this next. There are clever ways of doing this so that you actually can do better than n squared. Not by a whole lot. It's like n log of n or something for quicksort, I think. Is that right for quicksort? It's n log n. Do you remember from data structures? Okay. Well, anyway, right. Look up what the order is. I'm pretty sure it's n log n. But yeah, anyway. So in algorithm analysis, which is a huge sort of subcategory of theoretical computer science, this is a really big deal, right? You have different algorithms and you want to know how long do they take to run? Are they on the order of n squared or n cubed or something more horrible? Or can you, if you're clever about designing the algorithm, come up with ways that run faster even with large numbers of inputs? Okay, so that's sort of the idea. Okay, yeah, worst case. Well, okay, yeah, worst case is always n squared for this one, but what sort of average? Yeah, okay. Yeah, well, best complexity would be just n, or because if they happen to already be in order. Oh, right, right. With merge sort, it might not. It might actually take longer. But bubble sort would be best case in. Okay, so we'll spend the rest of class and also on Monday talking about why what everything that Owen and I just said to each other makes sense. Okay, and what all that means. Okay, so the next thing that we kind of want to do here is say, all right, with the case of our sorting algorithms, okay, with the cards, I never actually told you what algorithm to use. I just said sort them, and you guys all did it, and essentially you guys all ended up doing a variation of one of the slower sorting methods uh, called bubble sort. Okay, so bubble sort is what I want to talk about next, and probably the easiest way to explain this is, well, what's the bastion of all knowledge of Western civilization? Oh, it's .org, whatever. Sometimes that can actually get you into trouble. Um, for example, in the 90s, there was NASA was landing a rover on Mars, and so lots of schools were doing activities related to the thing. And so the kids went to the library and they have computers and the internet, and this is the big new thing, right, in schools. And they're like, oh, let's see what NASA's up to with this cool rover. And so where did they go? Where did they try to go? NASA.com. Where would you actually go? NASA.gov, right? Because it's a government organization. Well, NASA.com, let's just say, had other content. It was not a space agency. Okay, and a bunch of kids learned that the internet is a very terrible place, even in the 90s. And this is before 4chan and all of that nonsense. So anyway, okay, so let's talk about bubble sort. Okay, here's essentially the way it goes. So let's watch this animation and imagine that these numbers are your cards. Okay, so 6 was greater than 5, and so I'm going to have sort of this sliding window where I'm going to compare each card to the next, and I'm going to move from left to right, and I'm going to exchange the cards if the one on the left is smaller than the one on the right. Okay, and I'm going to keep going through the entire list. Okay, now they're still not fully in order, as you can see, but I'm sort of partially getting them in order. Okay, now did anybody actually do it basically like this? Probably not. Okay, all right, and then you start over, right? And it's called bubble because the numbers, sort of the bigger numbers, sort of bubble their way to the right, and you keep going back and redoing this process on the remaining numbers and get them in order. Okay, so then we're going to bubble once more, and then the 4 and the 7 are going to swap, and then we know that the 7 is in its final position, and then we'll go back and do it again and again and again um, until we're finished. Okay, so let's watch the rest of the animation, and this will kind of make some sense, right? Okay, now you guys can see that this is horribly inefficient, right? Um, but it's very easy to program. And it would be very easy to explain to somebody this procedure, okay? And so we're going to use this, even though this is the worst possible way to do sorting, we're going to use this as sort of a running example of how to analyze a particular algorithm, okay? So they're going to flop, and then the 5's in final position, and then we go back and keep doing it, right? Okay, so there's really two operations that are happening with this particular sorting algorithm. It takes us a step to actually swap the cards. Okay, so that takes work. It also takes us a step in order to compare one card to the next to determine, do we need to swap them, right? That may happen almost instantaneously in your brain when you got two cards in front of you, but there is a very slight amount of time that took. Same thing on the computer, right? Doing a comparison requires saying, doing an arithmetic operation. Are these two things, which one's less than the other, right? Okay, so now what we want to do is basically program this and see how it's going to work. Okay, so I've got some code that I wrote. Um, and so let me put these up on Canvas in the file section, and then we can copy them over here. All right, so let's make a folder for algorithm analysis, and let me take my, oh, come on, this isn't that boring, but it's Friday. Yeah, well, I can understand that. Okay, so let me download these these three Python routines, or four actually. Okay, and let's kind of look at them. Okay, So I don't need that one. Okay, so, all right, so here's basically the algorithm that we're going to use, right? I have programmed in here the bubble sort routine, okay? So what I'm going to do is I have an array of numbers, okay? And basically instead of queen and ace and stuff like that, I'm just going to think of the numbers 1 through whatever as being my cards, okay? And this is where the playing card analogy sort of goes away, that I'm going to start thinking about the number in as being the number of cards rather than the number of suits. Okay, but they're basically the same thing, right? One is just 13 times the other. So I could imagine, right, sorting an entire deck of cards using this bubble sort technique would be kind of like if I handed out cards that just had the numbers 1 through 52 on them and said get to it, it'd basically be the same thing as sorting the uh, the four the four suits. Okay, with one exception. What was it that you were able to do with the suit sorting that you obviously couldn't do if they were just numbers 1 through 52? Yeah. Yeah, you couldn't stack them, and you also couldn't separate out the suits and then sort each individual suit, okay, because there's no suits anymore. So that sort of acceleration or technique that you guys used would be off the table. Okay, so anyway, here's our bubble sort routine. Okay, so all it's going to do is you'll notice that it has 2 for loops, right? Because it's going to basically scan through pairwise, and it's going to keep doing that over and over until, like in the animation, everything's in its proper position. Okay, and it has to check um, if one thing is bigger than the next one, it has to swap them. Okay, and so I've got this number in here called ops, and the ops is just going to keep track of how many operations it took to do it. Okay, so what kind of operations do we have here? There's really 2 types: swaps and comparisons. Okay, and so here, this is a comparison. So that's why I put ops plus 1 right above it, because every time I do that, I'm doing a comparison. And then if the comparison means I need to swap something, well, then I'm doing a swap, and so I need to add 1 to my number of operations. Okay, does that make sense? Okay, and then I've commented this stuff out, and we'll see why in a moment. Okay, um, I'm going to, I made here an array. Okay, and just for sake of demonstration, I made my array the numbers 1 through 15 exactly in order. Okay, and what we want to see here is that when we talk about the complexity of an algorithm, we really can talk about several things: average case, best case, and worst case. Right? So think about this. If the numbers just so happen to already be in order, how many steps do you think it's going to take to do this? Yes, on the order of 15. Okay, so on the order of n, not in squared. Okay, so the best case for the bubble sort algorithm is that it's O of n, right? Because there's only 15 numbers there, and if they happen to be in order, I mean, granted that's exceedingly unlikely, but if they just so happen to be in order, then, well, there's not a whole lot to do. I need to do basically 14 comparisons, but 14 is basically 15, right? Okay, and I don't have to do any swaps because everybody's exactly in order. Okay, good. Now, what would be sort of the worst case would be, what about if I put all of these numbers in reverse order? That would be the absolute worst case that we could possibly get. And if you think about it then, so imagine that's 15 going down to 1, you're going to take the 15, and how many things are you going to have to do? Each time you're going to be doing a bunch of comparisons and a bunch of swaps, and you're basically going to be doing 14 of each, right, to get the 15 all the way to the far right. Okay, and then the 14, basically the same thing. Okay, So at worst case, it's definitely going to be n squared. And as we'll see, on average, it's basically n squared also, okay? Which is basically in line with what we did what we got when we were doing this, you guys with the playing cards, right? Roughly speaking, it's an n squared thing. Okay, so does that kind of make sense? Yeah, Gucci? Okay, so well, first off, let's just run this and see what we get. Okay, so 1, 2, 3, 4, 5, right, was my um, original array, and I printed it, and then I printed the number of operations it took, 105. Okay, and actually, hold on one second. Okay, let me actually do this version. Sorry, I rewrote it to okay. So I did I rewrote it a couple of ways. The first is I had it print out every single time. Okay, I can turn that off, but essentially, uh, this would be how I could make the animation from um, the Wikipedia article, right, with this sort of thing. Okay, so what do we notice here? What's happening to the 15 up at the top? Yeah, one spot each time. Okay, so every time it does that, every time it moves a spot, that took two operations, one swap and one comparison. Okay, and then that gets 15 where it belongs. It took 15, well, really 30 steps to do that, right? It took all of those steps to get the 15 into the correct position. And then the 14, the 13, and so on, right? Here's the 14 moving, and so on. And okay, a whole lot of work is happening, and eventually we get, in this case, it took 210 operations for that 15 thing, okay? Now, 210 is on the order of 15 squared, because what's 15 squared? 225, okay? And if we rerun this, okay, with, so in this case, let's see, I was using bubble 3 here. In this case, my array is a thing of, well, 15, the numbers 1 through 15 in order. Okay, so let me, if we rerun this, but I do the numbers 1 through 15 in proper order, how do you clear something to other than quitting and reloading it? Is there a way to re-import? Yeah, that's okay. We'll just re-import it. Yeah. Okay. So anyway, if the numbers so happen to be in order, then how many steps did it take? 14, right? And that's because there's 14 comparisons that we need to do, because each comparison is pairwise, so that's why it's one less than 15. But we don't have to do any swaps, everything's already in order, okay? So that's O of n. At bare minimum, if the numbers happen to be in order, it still takes 15, or basically 15 steps to do this, okay? And if I put them all in reverse order, then it would take, what did we see? Say 210 or something like that, right? Okay. So let's switch this up a little bit, okay? And let me quit, and let's go back to my code here, okay? And what I'm going to do is I'm going to comment this out. I'm going to comment this out, but I'm going to uncomment these out. Okay, so what I'm going to do here is, let's say that we're sorting 5 cards, okay? At minimum, how many operations would you expect this to take? 4, okay, if they also happen to be in order. At most, how many would you expect this to take? On the order of 25-ish, right? 5 squared, okay? And on average, about how many do you think it would take? Somewhere in between, obviously, but what we want to look at is how does that somewhere in between grow if we add cards to this, okay? So I'm going to do this for the sake of 5, or for the case of 5, okay? Oops. Oh, yeah. Python is really picky about tabbing. And when I commented, I introduced some spacing. Okay, so what this is doing is it's taking 5 cards and sorting them, generating 10,000 random arrangements and sorting those 10,000 random arrangements and keeping track of basically the average as we go. And okay, it took on average here 4 operations. That doesn't make sense. Did I screw up something in the code? Let's look. Oh, that's right. I didn't print. Okay. So I printed the wrong stuff. Okay. So I need to comment this out. I need to comment this out. I need to do this, this, and this. I was printing basically just the sorting of a single one of these random things. The very last one, okay, was what I was printing. Okay, and here, right there, I'm printing the arrangement. Let me actually turn that off because I don't want to just spam the terminal with a whole bunch of printings. Okay, so what I wanted to print, and sorry, this is my bad, is I wanted to print the minimum number of operations it took for all 10,000 of those tries. Okay, so what's the minimum that we would expect to see? 4, okay? And then I wanted to print the maximum that it took for any number of those trials, whichever one was the largest number, and that we would expect to be on the order of 20 something, okay? And then I wanted to do sort of an average, which is count up the total number of operations that were performed over all 10,000 tries and divide that by 10,000 because that's how many times I did it, okay, to get sort of an average case. Okay, so let's try this again. Okay, so it's going to take a minute to run this, obviously. Okay, and so what did we get here? We got on average, minimum, maximum, 20, okay, which is basically 25, and average 13.58, okay, whatever. All right, somebody who's got a computer open, go on to our Google Sheet, okay, and make a second tab, okay? And I'm gonna have you guys do the data entry for me because just to speed this up a little bit. So if we go back to our spreadsheet, right, make a separate sheet. Well, I'm doing that now. Okay, so on sheet 2, Kiana, you're gonna be our data entry guy, okay? On sheet 2, in the first column, so column A, put the number of um, cards that we did here, which in this case is 5, right? Okay. And column, or so actually put labels for the first column. So put that one row down. Yeah. So put 5 there. And then in the top column, put N, just the letter N. Okay. In row B or B there, put minimum or min, then average, and then max. and then put down the three numbers that we got when we generated this. And I'll go back to the terminal so you can see it. Okay, so all we're going to do here is basically record the data, right, from running 10,000 instances. And what I'll do is we'll go back into Python and I'll change this, instead of being 5 cards to being 10 cards. And then we'll just go 5, 10, 15, 20, right? Just that's enough to get the sort of idea as to what's going on. We don't have to do 5, 6, 7, 8, and so on. Okay, so does that kind of make sense? So it's essentially just what we did with the cards, except you're also keeping track here of the number of operations rather than the amount of time it took. Okay, but do you guys think that those are sort of reasonably equivalent things? Time and steps is basically the same, roughly? Yeah, reasonable? Okay, so that's what we got for 5. So let's rerun this for 10, 15, 20, 25, and a few more, right, just to get some good data. And let's see what happens. Okay, so I really should have written this differently. Okay, so I'm going to change this to 10. Okay, and obviously this is going to take a minute. All right, so minimum 19, average 61.50, and maximum 86. Okay, seem reasonable? Yeah. Okay, now I should be clear here. Is the maximum that occurred necessarily the worst case? No. Okay. But do you think it's probably going to be pretty close to the worst case? Yeah. Okay. So what is always the worst case with this particular algorithm? When does it occur? Well, yeah, but how did you get 99? If I had 10 cards and they were like, what would be the arrangement of the 10 cards if they were all sorted in reverse order when you started, right? So if it went 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, that's the worst possible case that we could get. Okay. All right. So let's do this. Kiani, did you get those numbers? Okay. So let's do the same thing. Okay. But let's do it now with 15 cards. Okay. 46 minimum, 145.23 average, 192 maximum. Okay. All right, so let's do it again. Uh, 20. Okay, so 20, 125 min, 265.78 average, 337 maximum. Okay. And again, the minimum here is not the theoretical minimum, because what is the theoretical minimum if there's 20 cards? 19, but basically, yeah, 20, right? And so that minimum theoretical value didn't occur because how was I generating all of these permutations? I was generating basically a random permutation, and if I've got 20 cards, what are the odds that they're going to be perfectly in order? Very low, right? I mean, we could quantify that, but it's going to be a very small number. Okay, so there's 20, and how about 25? Okay, 253, 423.00, and 534. Okay, and finally, let's do just a couple more here. 30. Okay, 343, 617.22, and 745. Okay, and let's just keep going. Obviously, this is going to take longer and longer the larger I make this number. Okay, so this was 567, 848.53, and 1,030. Okay. And we'll keep going up to basically 50 or 55 because that's basically the same as the number of cards in a deck, right? 52, just for sake of completeness. Yeah, sometimes computer science involves a lot of just sitting there and waiting. Sorry. All right, so what do we get? 754, 1115.83, and 1320. You know, if the professor was smart, he would have written a loop of loops here, but that would have been. I'll probably rewrite this code a little bit for next time. Okay, so we got that. Okay, so that was for how many? 40 or 45? Okay. That's good enough, I think, for our purposes. You guys get the idea, right? Okay, so what are we going to do on Monday? We'll start with just very briefly a recap of this. Let's look at the graphs for this, and also what we'll do is we'll think through really carefully why it is that the minimum number possible is one fewer than the number of cards. That part's obvious, but then also explicitly come up with the formula for the worst case scenario, um, the actual worst case, not sort of the worst case that was encountered amongst the 10,000 random tries. Okay, so make sense? Okay. All right. Well, have a great weekend, and we'll have some information for you guys about SI the Sunday and Tuesday session because, well, a few things. What are we doing Friday next week? An exam. And so when is basically every homework assignment ever due? Wednesday. And if it's not in by then, yes, you were boned. So, all right. See you guys later. Have a good Halloween.